Hi guys, we are continuing on with hypothesis tests here for the mean. We're going to do some with data and then we'll look at some other examples too. All right, so first up, here's one that has actual data. So the level of dissolved oxygen, which we are abbreviating DO, DO for dissolved oxygen, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. So here's our actual data. The average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Does the data provide evidence at the alpha equals 0.05 significance level that the aquatic life in this stream is at risk? All right, so we're asking for a significant evidence with a certain alpha level. So that looks like that tells us that we are doing a hypothesis test. And I kind of wanted to sneak the picture in here too for just to mix things up, but it doesn't leave me much room there. All right, so we've got that our mean is the true mean dissolved. I suppose I should just write DO. All right, they told me I could write DO right there. DO level in the stream. There we go. And let's see, alpha equals 0.05. Our null hypothesis is that the mean, so we're asking specifically about 5. So our null hypothesis we'll say is 5. So that means our alternative, and we want to know, is it below 5? We want to know, is it at risk? And at risk is below 5. 5 or more is okay. And this is in milligrams per liter. If we know units, we can put it, but we'll put them somewhere. We'll put them here in the end. At least that'll take care of it there. All right, and otherwise we don't have the other stuff. We have data. If you want, you can say n equals 15 because we have 15 randomly chosen locations. All right, so we are going to do, so this is only one sample, so that's a one sample. We are working with a mean, so it's t test. We're doing a test, not a confidence interval, for mu. Let's see, it says we took randomly chosen locations, so that would be random sample right there, taken care of. Random sample stated. Next up, normal sampling distribution. So it did not tell us the population is normal. We don't have more than 30, so this means we need to look at the graph. And to look at the graph, we got to put it in the calculator. Or we got to try and graph all these by hand somehow. All right, so next up, I'm going to go to the next one, then I'm going to come back to the graph. So independence. So our sample size is 15, which is surely less than 10% of all locations in the stream. Right, that would be our population would be anywhere in the stream we could choose from. So as long as there's over 150 different locations, we can always move over just a little bit to the left, a little bit to the right, whatever. Like we can be right here, or we can be right over here, or right over here. You know, we can hop to the other side and then maybe off of that rock, you know. Plenty of locations there. So now we need to look at the graph. So one way to do that would be to put all the numbers into a list. So here's edit, and here are all my numbers in a list. I put them all in L1 already. Right. So now if I want to graph them, I don't know what I've been graphing on here lately, but let's just go here to L, or the stat plot, and choose the first one. And it looks like I've got it set on box and whisker showing outliers, which is good because I want to know if there's outliers, right? And blue is fine, so let's take a look at the graph, and let's go ahead and zoom 9 to get the stat graph. There it is. I got some other stuff going on in the background here too. I don't know what I was graphing in calculus. But there's our box before the line goes right through the middle of it. Oh, let me get rid of those. Oh, that's a horizontal asymptote. I don't know if I need that anymore or not, so I'm going to leave it there. There we go. But there's our graph, so I'm just going to draw a little sketch of that. It doesn't look very skewed. There's definitely no outliers. So we're going to say no outliers. Not strongly skewed. I mean, it can even be skewed a little bit, but not strongly skewed is what we're looking for. So both of those check out. So that means we have an approximately normal sampling distribution. So that checks out. Whew, a lot of stuff there. All right, so now we're going to our calculator and we are doing our t-test. All right, so let's see. I've already got the data put into L1, so that's good. And I'm going to go do a t-test. And now I am working with data because I don't have the mean or the standard deviation from the sample. So I'm just going to select data. And now it just wants to know what's my null hypothesis about. And my null hypothesis is that it's equal 5. My list is L1. And my alternative hypothesis is less than. If I go back over here, it does say less than. That's already highlighted. Cool. And we'll go to calculate. And now we just write all of it down. All right, so we didn't have the sample mean written down before. We didn't have anything. So we're going to write down everything. So t equals negative 0.94. So t equals negative 0.94. We want our p-value. We got our x bar. We want our standard deviation. We've already got n. But again, we can just write down everything. So p is 0.18. 0.18. Our sample mean was 4.77. 4.77. And the reason we're writing down all of this is so sometimes they ask for it on the AP exam, and then sometimes you'll use this on like a question going forward. So 0.939, I guess, will work. 0.939. If you want to say 0.94 because there was a 5 after that, that's fine. That works too. It's not a rounding test. All right, so now we're going to compare our p-value to our alpha value. And we're going to say since the p-value equals 0.18, which is definitely greater than 0.05, which is our alpha, let's see, p is not low, so we fail to reject our HO, that the mean equals 5 milligrams per liter. So in other words, we do not have significant evidence of the alternative. We do not have significant evidence that, and we're going to put the context in here, so we're going to go back and we're going to say what this mean stands for, that the true mean dissolved oxygen level in the stream is less than, our alternative hypothesis, less than 5 milligrams per liter. All right, so we don't have evidence of it. So that means we're good, actually. That means the water is okay. Or we don't have at least strong evidence that the water is not okay. All right, here's another example. So at the Hawaii Pineapple Company, the mean weight of the pineapples harvested from one large field is 31 ounces last year. So this was the mean weight from a large field last year. A different irrigation system was installed in the field after the growing season. Managers wonder if this change will affect the mean weight, again talking about mean weight, of future pineapples grown in the field. To find out, they select the weight of a random sample of 50 pineapples from this year's crop. The sample has a mean weight, so sample mean, of 31.935 ounces with a standard deviation of 2.394 ounces. Use alpha is 5. All right, so we're asking about mean. They're asking us for significant evidence, so that means we are doing a hypothesis test for the mean. So we're going to say our mean is the true mean weight of, I guess we can just say the pineapples. All right, it's in some particular field with some irrigation system, but to save time, we'll just say the pineapples. We've got alpha is 0.05, 5%. We've got the mean of the sample is 31.935. We've got the standard deviation of the sample is 2.394. And we've got that our sample size is 50. Hey, 50 is good. We like 50, nice and big. All right, and we need our hypotheses. So our null hypothesis is what it is from last year. The mean is 31 ounces. Our alternative hypothesis, let's see, different irrigation system, they want to select blah, blah, blah. Wonder if this will affect the mean. Well, it doesn't necessarily mean greater than or less than, so we're just going to say not equal to 31 ounces. All right, so affect means is it going to be different? All right, so we have one sample. We are going to do a t-test for the mean. So we need to have a random sample. And it is stated up here somewhere. There it is, random sample. So that's stated. All right, for the normal condition, n equals 50. Hey, that's good. That's bigger than 30. So by the central limit theorem, we have an approximately normal sampling distribution. Oops, started writing normal again. Approximately normal sampling distribution. Check. And independence. So our sample size is 50, which is hopefully less than 10% of all pineapples in this field. Usually the pineapple fields are pretty big. As long as there's more than 500 pineapples on this plantation, we should be good. All right, so that checks out as well. All right, so now we're going to go to our calculator and we are going to do a t-test on our calculator. So on stat test number 2, t-test. All right, we are back to having actual statistics now because they gave us the numbers instead of the actual data. Let's see if I can get this right this time. The null hypothesis is that it equals 31. Hey, our alternative or our sample mean here is that our mean is 31.935. Our sample standard deviation is 2.394. Our sample size is a pretty good size here, 40. And we want to know about not equal to. That's the first one, so we'll press enter on that one and calculate. And there we go. T is 2.47. And our p-value is, let's see, what was it? 0.0179. So 0.018, I guess, would work. 0.018. And we've already got the sample mean and the sample standard deviation and n written down, so we don't have to write them down again. But we do need to write down both of those. So there's our p, and we're going to compare that to alpha. So this is basically 0.02, and this is 0.05. So since our p-value equals 0.02 is less than 0.05, which is our alpha, so p is low, it's lower than the alpha, so we reject the hoe that the mean is equal to 31. I started writing ounces already. 31 ounces. So that means we have significant evidence for the alternative. So we have significant evidence that, and we need to have context, so we say what our mean is. The true mean weight of the pineapples is different. Notice I'm using present tense here. Is, not was, is different. Is different from 31 ounces. And there we go. All right, another quick one on your calculator here. So if it's multiple choice, we can do it pretty quickly. So we've got burgers we want to know if burgers are significantly different from the industry standard. We have a mean of 12.5 ounces, which is a pretty substantial burger. He takes a random sample, that's taken care of 35 CLT, works normal, and weighs them before they're given out to the customers. He finds his sample of burgers have a mean weight of 12.8 ounces with a standard deviation 0.08. At alpha equals 0.05, what should he conclude? All right, so again, we need to check what the hypotheses are. That's the important stuff here. So we've got a mean of industry standard is 12.5. We want to know, he takes a random sample, where they're given out to the customer. He finds his burgers have 12.8 ounces. Wants to know if the burgers are significantly different. All right, so he just wants to know, are they not equal to 12.5? All right, so now let's see. Here's our x bar. Here's our s. And here's our n somewhere. There it is, n. And we can just throw those into our calculator under stats. So let's see, stat, test, t-test, and let's see, we do have statistics. Our null hypothesis is 12.5. Our sample mean was 12.8. Our sample standard deviation was 0.8, pretty small there. Our sample size is 35, good size sample. And we just want to know, is it different from? So not equal to works, and calculate. And we get that our p-value is 0.03. All right, which is less than alpha. So that means we're going to reject the hoe, all right, because p is low. So our p-value 0.03, we reject the hoe. There it is, B. All right, so that's it for this. And the next one, coming back, we're going to look at a pretty difficult concept called power. All right, so come back, 8.3, Part C for power.